Thank you. Provocative is quite the euphemism, huh? When you provoke, that's when the people throw tomatoes at you. Actually, so what Jacob was exactly correct. My starting point for this whole stream of work, and there's a lot of it here, so even though there's not that many slides, please interrupt me. I myself will sort of get confused. There's a lot here, so let's ask questions. Let's make it be a dialogue. To put in a plug for a whole bunch of other work I'm involved with, Hayek even said the market is the computer. You can go back to Adam Smith, and if you don't really read him too closely, the whole notion of the invisible hand, more broadly, especially if you happen to have had your mother's milk at the Santa Fe Institute, there's this notion that social systems compute. Okay, cool. They're all computers, nice as a metaphor. If you look, actually, this is now a plug for a completely different body of work. Let's create this one. But is there actually any field of science that actually would maybe put substance behind the notion that a social system is a computer? Yes, there is one and only one. It is called computer science theory. Great. Let's look at all the papers that have been written about the computer science theory of social systems. It's the empty set. So I'm not going to be talking about it today, not directly, but just a plug for a whole nother body of work I'm doing with this a great archaeologist, Kyle Harper, and James Evans, who Jacob knows, of course, very, very well, and many others, other physicists and so on. We are taking computer science theory, computational complexity theory, and applying it to social systems. So anyway, that's a plug. But here, I'm going to be actually just taking the computational power of social systems as magic. I'm not going to try to understand it not directly. I'm just going to take it as given and see what that can do for distributed control and then distributed optimization. So let's start with taking these concepts. Social systems, one of their key characteristics is that they are distributed systems. They are implementing, if they're doing any kind of control or optimization, it is distributed control, distributed optimization. Okay, cool. Where does that get us? Well, it turns out you can take, this is a roadmap of what I'll be showing. You can take these general ideas and adapt them for distributed control of multi-agent systems. So back when I was at Stanford and NASA, me and my grad students would fly around swarms of drones above Stanford campus using these kinds of ideas, and I'll show you some other movies of these kinds of things. Basically, the idea is each agent, each robot or what have you, it's running a reinforcement learning algorithm. Just like every human being is running your own reinforcement learning algorithm, at least in the caricature of Adam Smith's invisible hand. Our trick is to design the reward functions of each of the agents so that the Nash equilibrium of the resultant game optimizes whatever we want the overall system to do. So a way to view this anthropomorphically, I take all of you, and what I want all of you to do right now is nominate me for a Nobel Prize. I'm going to get that by going into your heads, modifying your reinforcement reward signals, your utility functions, so that as all of you are being what you think is completely greedy, my overall welfare function for what I want all of you to do is actually optimized. Bummer, I can't do that with you folks out there, but you can do it with robots. And this is actually a powerful way of doing distributed control. So I will start with that. You can then take these techniques and not just view it for distributed control, but for distributed optimization, because after all, control means you're trying to optimize an overall control function, objective function for your system. I will then talk about how things like what's called the cross-entropy method, genetic algorithms, simulated annealing, these are just special cases. You can do much better than all of them, and I'll show how. But before getting to that, I'm going to start by relaxing the requirement that the implementation of your ideas be done in a distributed way. The laser doesn't seem to always want. And once you do that, it turns out there is a formal correspondence, an isomorphism, I guess at least in the sense of category theory, between optimization and supervised machine learning. And what that means, and I'll end up with this, is that you can take all of the techniques of machine learning, all of them, and just translate them. It's like a dictionary. You translate them into the context of doing optimization, whether if you want to do GAs, simulated annealing, you can do any of those with these as well, and improve them. So that's where I'll end. So, as I said, a whole bunch of stuff here. Please interrupt me as we go. Before we actually launch, is there anything that I should sort of clarify about what I've said so far, or just sort of start to do it? And that then will be giving you meat to chew on.
David, could you start by helping me out
a
little bit? Hi. Could you start by helping me out a little bit between what you mean by machine learning versus optimization?
Yes.
A lot of machine learning is optimization.
Yes, but of a completely different point. The dumb way of doing this is, let's say I've got a bunch of different optimization algorithms, a bunch of GAs with different parameters. You can imagine giving them 2 data sets that you want them to find the optimal among those points. Whoever does best, fastest, that's a version of cross-validation. You can do much, much better. The correspondence is much better. So it's not, what you're thinking of is using optimization to do machine learning. You don't need to optimize. If I'm doing a nearest neighbor algorithm, kernel density weighting, I'm not actually optimizing anything. I'm just trying to find my nearest neighbor, and I go with that as opposed to parametric. This is going the other way. Taking techniques like bagging, regularization, all these techniques that you use in supervised machine learning, porting those over into optimization. So it's going the other way. Good question. Okay? All right. This is the golden rule. This is economics, game theory, very first 15 minutes, the very first day of the very first course. Every agent, this laser does not want to work. Every agent, every player in the language of game theory, in an economy, they don't actually find the value of a variable. They've got a variable that they can control, what's called your pure strategy in game theory. They don't try to search for the value of the variable that optimizes some particular function. They want to find a distribution, what's called in game theory a mixed strategy that optimizes the expected value of the function. This seems like a distinction, a difference of no distinction, or however way the phrase goes. Because after all, a delta function about the optimizer of g of x is going to optimize expected g of x. What are we getting by actually viewing things this way? It's a very, very trivial concept. It would seem to be having zero consequence. Well, it turns out that there's an entire field called Monte Carlo optimization, which actually is based upon this. It's a standard optimization technique. You start with an optimization problem over x. You just turn it into an optimization problem over a distribution by saying that I want to find the distribution so that expected value of, say, g under that distribution is optimal. You can solve for a distribution from a data set much more readily than you can solve for an actual optimal point. So if I've given a bunch of data points, input-output values, it's much easier in many, many senses for me to use them to say this is a distribution over the input space that I think is optimal. And this is, in fact, what genetic algorithms and things like that do via hacks. Every time you have a new generation in genetic algorithm, it is sampling from an implicit distribution. So to invert, to go from a distribution to a particular point, you just do a sample. So let me, let's see, talk about GAs in the next place? Yeah, so here are 2 examples, GAs and simulated annealing. At this point, probably a lot of people are confused, but so let's go through this. Let's make sure we get through this slide and people are at least not too confused. Let's say that I want to optimize the value of a function g of x. Let's say that I have some way of producing a distribution over x's from data at a iteration t. Call that the data at the iteration t is d of t. This is an iterative algorithm. This is black box optimization. So what I do is at iteration t, I'm trying to do black box optimization. If you're doing simulated annealing, this is actually pretty explicit. I find the distribution that optimizes expected g conditioned on the data set minus a temperature times an entropy, a Boltzmann distribution. That's what motivates simulated annealing. You then sample from that distribution. This is a step of simulated annealing. You sample from your distribution, add those samples to your data set to get a new data set, and then you repeat. What you're doing in simulated annealing, you're always working with distributions. You're never working directly by doing something like hill climbing to try to find a best point. Genetic algorithms are the same thing, except that this is implicit. We do that by actually generating a new population. That population is a bunch of samples of new inputs. In the naive GAs, you produce that new sample, your offspring, you see how well they do. That data, these offspring did that well. They go into your bigger data set, and then you do something like this to try to, depending on your what's called the annealing schedule for your temperature, focus in on those offspring who are doing best. There's actually a body of work produced by some people in Spain, I forget who, they call it Evolution of Distribution of Algorithms, which can be viewed as related to all of this. Okay, Unimate, go for it.
Just a little mixed up because the population in a GA, anytime I get it, is a sample. It's not a distribution, right?
Well, but there's implicitly a distribution is produced from, because you produce your offspring randomly. So therefore, there's implicitly a distribution of the offspring, and you're generating a sample of it.
But I've also got selection, right?
Then at the next step, you might actually say, then you add those offspring to your current data set after seeing how well they do, and then you can at the very next step, in GAs you don't actually have a entropy function, you've got more like a threshold function where you get rid of those who are not doing well and only pay attention to the others.
Yeah, I mixed up because really in a genetic algorithm you have a finite population.
These are all
You have a finite search space.
The search space.
Like a distribution.
Because when you produce the offspring randomly, I do a random mutation, I do a random crossover, I do all kinds of random things. As soon as I see the word random, there's a distribution there. And you're taking a sample of it. You just don't think of it in those terms.
It's a biased sampling algorithm.
Oh, yeah. And so is simulated annealing.
And so it's really only in the first generation.
Well, after that as well, you're always, however far you go, in your super cool work on software, when you're just randomly exploring the neutral mutations or whatever, the key word is random. Its exploration is going on as well as exploitation, and the exploration, almost by definition, is a random process. Therefore,
I don't think we want to disrupt your talk, but I think Uname and I are picking up on the fact that the actual distribution that you're sampling from changes over time.
Yep, and that's true here as well. That Q of X, that Q is actually sub T. That's the whole point. In simulated annealing as well. You
have no T in your Q.
Yes, you're correct. That should have a sub T. At each step, you produce Q of X from the data that iteration. So this should be a Q sub T. You're exactly correct. But the distribution is updating. And one of the cool things about a GA...
Don't let us distract you.
No, it's cool. And one of the neat things about GAs, of course, GP, all evolutionary computation, is that you never actually need to have the distribution explicit. It's only implicit. But it's there. You can never actually, nobody ever bothers to write it down, because why? here's my distribution, and then I just sample it, and then I go. But with
I think
things,
there's been a lot of debate over the years about what distribution you're actually sampling. But let's talk about that later.
that one could throw that into the mix as well. I'm not going to try to plonk for one or the other. I'm pointing out that both simulated annealing and these evolutionary computation approaches, they involve implicitly or explicitly underlying distributions that they are now optimizing by a process where you're sampling those distributions to get more data.
Optimizing or searching?
Because you're searching for the best solution. Now you're getting pedantic, Stephanie. Okay? Cool. I'm not going to be using GEAs or simulated annealing, so no reason to get too sensitive about that. So that's fine. That's but what do we actually mean when we say distributed optimization? Let me focus on that word distributed now. Going back to Hayek and Adam Smith and so on. Game theory, economics. A sort of N agents, a joint move. Since they're distributed, and they're all actually optimizing by having distributions, by definition, the joint distribution over everybody is a product. It's a product distribution. That's what we mean when we talk about a mixed strategy profile in game theory, if anybody's ever taken a course in game theory. So each agent optimizes their own expected value of G, and then they try to directly optimize X. This is a type of, I've not yet defined Monte Carlo optimization. I will in a little bit. For those who know more about game theory, this is actually what's called an exact potential game, sometimes called a team game, and so on and so forth in the literature.
So when you take a product of distributions, usually it means the distributions are independent.
Yep.
So how are these agents independent in the sense in the economy, certainly what someone else does influences me?
It's called a normal form game that at each stage, I am making a move simultaneously as you do, but then we each in the next stage see what the others have just done, and we then do our own internal optimizations, and then we then sample again. That's the vanilla version of what's going on in the human economy. It's what's called normal form or strategic form games, that everybody moves simultaneously. Prisoner's Dilemma. Think of all of your standard simple ones, hawk-dove games, the games of chicken. Everybody moves simultaneously. If you want to be, so that I get to see what you've done, and therefore by that we get to coordinate, that's because you now have a multi-stage game, where at each stage we are simultaneously making moves based upon we both saw concerning the other player in the previous round. And under this model of a human society, that's what's going on, folks.
So, I mean, you've brushed off the difference in search and optimize, but here I'm a bit confused because the question is, I understand what you're saying, that we're sampling each agent is sampling a distribution here based on others, but the question is, are they actually optimizing something in doing that? I mean, are they doing that, like take the genetic algorithms, for example. I understand what you're saying, that you have a new distribution at each step, but why is that exactly distribution optimizing some objective? And also here, is it always the same?
You are searching for something.
And when I'm searching for something, I mean, the whole goal is to search for something, but the way I'm modifying the distribution at each step, or here, the way the agents are responding at each step, why is it clear that it would be the same thing to say that they're doing some, they're modifying it based on some update rule, as opposed to saying that they're modifying it to optimize some local objective or utility?
I'm not quite sure. Are you saying that?
Take the genetic algorithms, for example, right? So the question is, if every choice of distribution, every type of response rule is not, so if I am optimizing something, any type of time I'm optimizing something, it defines a rule for choosing the next step or whatever. But the other way around is not clear to me.
Stephanie translated a question from the audience by saying, that's what in my world we call a fitness function. Now, that's what in my world we call an objective function. Does that help? Because that's what GAs do. That's what the search is for. You want to find the optimal, the fittest, i.e. the best objective, And in an economy, everybody is trying to find the one that's best for themselves. Under the Adam Smith view of things, we're all greedy bastards.
Yeah, fine. But the update rule you're doing in GA, the update rule you're doing in each step is not choosing distribution that has the best fit over all distributions. You're choosing it in some specific constrained way.
Oh, that's to be. I'm not saying that. Let me be very clear. I'm just talking these slides here. This is most overt in the case of simulated annealing. Yeah, my point was more generally, maybe I should have put like genetic algorithm in scare quotes. GAs are doing this kind of a thing in that there is an implicit distribution as opposed to things like hill climbing or something like that where you're explicitly taking, here is my suggested solution, not quite. Here is my suggested solution. In these other things, there's randomness. Whenever you got randomness, that means there's an underlying distribution. So, point taken. I should have had GAs here a bit in the scare quotes, especially for this audience.
Okay, so that I understand. But you are looking at cases where the update is given by some local, optimizing a local objective, as it is in these economic systems.
Well, I'm right now defining a distributed optimization problem. I'm not given this version of this talk before, so I'm learning as I go. Apologies because I might be squeezing too much in. But yes, because I'm actually going to weaken the whole point of distributed in a little bit. So it's maybe I'm going one too many steps at a time. But anyway, here's an example. Let me now not talk about what simulated annealing is and GAs sort of are. This was called a bunch of work that I did with my students at Stanford and then Brendan Tracy. He was a postdoc of mine at the SFI. It's called probability collectives. Define Q star as being the minimizer if we're trying to minimize, expected value of G minus your temperature at that time times the entropy of your distribution. Simulated annealing, the vanilla version of it, at any iteration T, it is trying to construct that. It's the Boltzmann distribution. That's what it's trying to construct, is the Boltzmann distribution. It then samples from the Boltzmann distribution, and you see how well you do. You use that to increase your data set, augment your data set, and so on. But in distributed systems, we cannot actually directly try to find that Q star because it's coupled. So this would be equivalent to trying to say that I want to optimize the performance of everybody in the United States in terms of, say, GDP growth. That I'm going to do by simulated annealing. But the Boltzmann distribution, where my energy function is GDP growth over everybody in the US economy, is not a product distribution. So I've got to actually turn it into a product distribution. So what we do is we search for the product distribution that is closest to the goal of simulated annealing, which is a joint distribution. And then we actually then used a mean field approximation. And now let me hopefully put some of the doubts to bed by showing this in real airplanes.
Does the trying to make it a product distribution correspond to an assumption that you don't form companies or groups of people with common goals? Would it correspond to that same kind of assumption?
Very much so, yes. Yep, individual agents. Yep, and that's got to do with hierarchical distributed control and so on. Let me now hopefully, how can I do this on this thing? There we go. Okay, so what you're seeing, this was he was actually a postdoc. What you're going to be seeing is the backside view. Can I actually pause this? This is actually a wing in a wind tunnel test. There are 4 agents. Those are what are called bang-bang controllers. They can be up or down. That's it. We saw it before. The wind speed was above flutter. That wing was fluttering like this. You do not want to be on an airplane if the wing is fluttering. Take my word for it. These controllers, they're binary controllers. It's called bang-bang in control theory. Each one of them is an agent running this algorithm where it doesn't even know the other ones exist. It's just getting a reward signal. The reward signal is from a global accelerometer. So this is, you are a person in the US economy. You are not doing anything except getting a particular function of US GDP growth. That function is your paycheck. You can see the speed is going up and up and up. This is far faster than you can do with standard control techniques. It actually got to the point where hardware limitations, these bastards who are adaptive, this is all adaptively done, they were going up and down. What they needed to do is too fast. I would not want to be in this economy or in this particular airplane. If I got to this particular point, I might not want to be in this country in 2 days, but that's for an election to decide. But that's what happens when we pass the hard limits. This is faster than you can do using any known standard control theory technique. Each of those agents was completely independent, just using a very, very simple reinforcement learning algorithm to try to do that version of simulated annealing I described before. That's it.
Quick follow-up to what Mark was asking earlier. So you're assuming there are no repeated interactions, basically.
In this, so far, what I've shown, that is the case. I'm not assuming it, I'm imposing it. That's why distributed control is for all megalomaniacs. I can't actually make you do what I want you to do, but I can make my little robots do what I want them to do.
I think that's what kind of throws us off about comparison to human interactions, because that's usually repeated over long periods.
But these are actually, if you think about it, there is indirect here, just like with humans, because those robots, they're learning, I do this, what's my reward signal? Well, it's going to depend upon what everybody else is doing. Indirectly. The key is how you craft those reward signals. It's going to depend on what everybody else has been doing before.
So normally when I haven't, not normally, but typically when I think of spatial systems computationally, I think of them having two modes of communication. One is I can say that everyone sits where they are, but they interact with their neighbors. And because they're overlapping neighborhoods, what we see is like a signal communication through the array, right? The second way I could do it is nobody moves and talks to each other, but they kind of emit something to the subsurface, a substrate on the surface, and we all pick up a gradient that's moving across the system.
Or I could just.
Or I could put one guy on my spatial system, and I can move it around, right? It can trot around a spatial
Or you
system.
can just talk to me. There's another way of doing it as well.
Right,
Signaling.
but your guys are not communicating. So what they're doing is they're sitting on this spatial system, because there's four of them in a row linearly. They obviously have impact on each other, because you're going to give them a global signal.
Yep.
Right? You're going to
Well,
say,
they're
I'm going to
actually,
give you
each of them
some
gets a different
flutter-related global signal.
But they're related,
And they
yes.
all have to, with their reinforcement learning, find a reward function for their reinforcement learning.
No, a move for the reward function given, but that's defined in their reinforcement learning.
They don't find, but they have to adapt their reward signal so that they get this.
They aren't adapting their reward signal. They're adapting their move. I, the designer, give them the reward signal. They are trying as best they possibly can, like in standard reinforcement learning. Those are reinforcement learners, very simple ones. They are just trying to figure out, do I want to be up or do I want to be down, based upon reward signals that I am feeding them.
And it's global, but it's about a global phenomenon that the four of them are all involved in, right?
Yes.
It's going to be the global phenomena of the wind speed across the array of the four of them or something.
There's a global
Flutter speed of the
accelerometer.
storm.
Yep, exactly so.
Do you train one policy for each one of them? Or?
Each ones are completely independent. They don't know that one another exists.
Okay, so what if you trained one policy just distributed to all of them? Would it have the same effect? All of them are collecting data, but you're training a single.
It would do much worse. Here's another analog. Let's say, I'm going back to that example, let me give it in a different way. The human economy, the US economy. Let's say our goal is nothing else but maximize GDP growth, okay, for the next year. I could give everybody in this room, your paycheck is going to be based upon the GDP growth of the country as a whole. The system is going to flail. It's going to be like this. The reason is that everybody's got a huge, huge signal-to-noise problem. Yeah, you're affecting the GDP of the entire country, but you can't see that. So the market is the computer, the invisible hand. What all of that is really saying is that That's not your reward signal. Under the invisible hand, there's this very, very small dimensional projection of the global GDP onto your paycheck. You are working with just that particular reward signal. I'm working with the one given by my paycheck, Jacob and so on in this caricature. We all have actually independent reward signals that are all based upon the GDP. If the GDP gets really bad, we're all out of jobs and our paychecks go to zero. So that is what's going on here. The magic, supposedly the market does this well. There are issues, but the market is the way that we take that overall social welfare and it gets farmed out to different reward functions for the different heterogeneous agents in the overall system. But so if you were to follow the same policy that I do, or vice versa, we would both be kind of blank out of luck.
Yeah, so what I had in mind was actually once you train a single policy, then you're collecting more data to train that one single policy.
You individually are doing that, and I individually are doing it, but your policy ain't mine.
But that depends on the observation, right? I could
And we
have
have
one.
different reward signals.
Right.
Your paycheck is written by somebody different from mine.
So the rewards are different here. What are the observations here?
These ones don't have any observations. They're blind.
So what's the policy? What is
You
it?
have a reward signal. Standard
So
RL.
just based on the reward. Well, usually in RL you choose you have
You have a
observations
move.
to an action based on to optimize the reward, but you have some observations.
Not necessarily. You just
No,
can make a
that-
move. You can just do a dump. These are the dumbest possible
Okay, so
things.
there's no pretty null
And it does
observation.
better than any standard control theory algorithm. A lot better. And this is as real world as you can get, modulo putting this on an airplane. We talked with Airbus, but they actually didn't want to do it. They value their airplanes, I guess, or something like that.
What if you take one of them away? Is it a resilient and robust system?
If you were to, we actually did this all the way up to 16 of them. And 16 was performing better than just 4. If while it's going, you just kicked one out, it's all adaptive, so I assume that there might be, because it's, talk about a nonlinear system, in this one, if it gets a little bit out of kilter, it might be that before the overall system restabilizes, all blankety-blank breaks loose. But modulo those kinds of effects, it would just then readapt. You kick one out, then rather than 16, you've got 15.
So when you showed us this, had they learned or were they still learning?
They were learning the entire time. That's why, notice that they're going up and down. Their actions are only be up or be down. If I'm going to flip my state, that's because I'm concluding, oh, I'm in the wrong place. I'm doing the wrong thing.
I'm just curious, like, why do some of them go fast and some go slow if they are still getting...
I assume that's got to do with all kinds of aerodynamics that I don't know, turbulent flows and so on. We're in a bad regime here, I assume.
Do they ever accidentally synchronize? Which I assume would be bad for this problem.
We never searched for that specifically. If they did, we never searched for that specifically. Good question. Very interesting question. Don't know. Okay. Does this is actually for my edification for how to give this talk better. Does this actually clarify what I was talking about before a little bit better?
No.
No. Okay, well, never mind that then.
But it's a very cool
See how
example.
you-
It's a very cool example of the blah-blah-blah-blah.
Can you say how the entropy goes
Sorry?
into? Can you say why these guys involving entropy?
Oh, the
changes?
entropy is so you do your exploration as well as exportation.
Why these? How
Just
these
like in simulated annealing.
so these guys knowing about like you subtracting off that temperature of entropy term is
If
important.
you cranked up the temperature just like in simulated annealing, eventually they would just be up or down purely randomly, which would not be good. So in those experiments, we had to keep we got down to a temperature and then we had to keep it fixed there because it was such a non-stationary system. They always had to be doing some
I think what I'm
exploration.
saying is, I think for connecting this to the previous slide, it would have helped me to understand how that formula corresponded to what made them good.
Can this even work for me? Oh, there we go. Okay, yeah. So this has got to do with what's called the annealing schedule. for the temperature. And normally, in simulated annealing, you try to run that down to 0. So your distribution, at the limit, your distribution becomes a delta function, and it's only then that what you've done is find the x that maximizes g of x, as opposed to find the distribution that is optimizing this particular approximation. What we were doing, because it was distributed, we weren't actually able to just do this directly. That's the Boltzmann distribution. We were using this. We were solving. You can solve for this mathematically. We were solved because we have a distributed system that we want to have it implement a joint Boltzmann distribution. By definition, you can't, because a joint Boltzmann distribution is not a product distribution. So you instead solve this. I'm leaving all that out. And then we did a mean field approximation, and you end up at the end of the day, a bunch of math. And you end up with something which I was then showing what it was implemented in. So it's simulated annealing, implemented in a distributed way, so you've got to approximate various things. Got it? Cool. Yep.
You're a big picture thinker, so if you help us, maybe we're losing the forest for the trees.
Pretty cool trees, though.
Is your claim that, there are particular engineering cases where distributed agents with very dumb RL rules can do great? Is that the claim? Or is it something bigger that you're actually saying?
I'm saying something much bigger. I'm saying,
Missing that connection.
yeah, so what I'm saying is in a human economy, the whole notion of a Nash equilibrium, it's what's called a mixed strategy profile. Every one of the agents is actually is sampling a distribution. They are not making individual moves. And in fact, there are many games that have no Nash equilibria if people do just some specific moves. Rock, paper, scissors, all these kinds of things. There just is no solution in what are called pure strategies. Everybody has to be doing a distribution. If we take that and think about that in the context of optimization and control more generally, we notice, oh, look, simulated annealing is working on distributions. I would argue evolutionary computation, it never has the need to make those distributions explicit, but it is always doing the same kind of a thing. There are other things like the cross-entropy method and a lot of other techniques that are actually doing that. So what I'm doing in this talk is saying, well, if we take that, put on that hat, and just run with it. Think about optimization more generally explicitly as something where you want to be optimizing a distribution rather than implicitly, like in the case of those other things. Where does it get us? And I've shown so far just some of the early steps along that way. Does that help, or does this make it now completely opaque?
I'm going to wait for the rest of the talk, because I think I'm still missing the connection or the bigger picture claim.
Okay, yeah. Probably I am as well.
It could be me.
Yeah, just fooling myself. How am I for time, by the way? Probably very, very bad.
You have 20 minutes total, although you have been taking lots of questions.
Yeah, okay. Go through our movie. There we go. There's a problem with I've just shown you. It works well. It works very well. But in general, we must estimate, every agent must estimate this expected G given its, every one of its possible moves from the data. Okay? How does it do that? We were just histogramming it. The problem is, think about every one of those microcontrollers. It is looking, the way that we were doing this, the naive way of doing it, you got this entire data set, everything I've seen so far. I have seen that when I'm in the down state, this is my reward signal. I've seen when I was in the up state, this was my reward signal. But some of those data points are from real long time ago, when everybody else was doing completely different kinds of things. So that data from long ago really shouldn't be affecting my decision process nearly as much as the far more recent data. In what I show you, we hacked that particular issue. What we did was we just aged the data so that we wasn't doing just a straight reinforcement learning. The data set actually paid more attention to more recent points than to older ones. Exponential weighting, decay of the importance of the data, a complete hack.
Well, it must be related to, in reinforcement learning, because it's temporal, you have an exponential decay on your awards from the past.
We're doing the exponential decay on the data from the past.
But in reinforcement learning, you do that with your reward, right? You temporarily discount your
Oh,
rewards.
that's what it amounts.
You temporarily discount the states that are farther away.
Yeah, not
you
the.
get the reward and it's delayed, right?
Yeah, that's what I mean. The data points were action reward pairs, and we didn't do things like take their average. We did things like take their weighted average, exponentially weighted. Hack, complete hack. And this hack, the problem is, as you try to blow this up to much bigger systems, that hack starts to bite you. So here is the way that we got around it. We said, let's not be so anal retentive about being distributed. Let's see what we can get away with if we're just trying to optimize distributions. This is actually where Monte Carlo optimization, I should have first defined it. Turns out there is a field already in optimization theory, in engineering. It's actually amazing how much is already there in engineering that we nerd scientists, or at least anybody in the room who calls himself a scientist rather than an engineer, we're always rediscovering it. We think we're so brilliant, but engineers have been there long ago. But in any case, Monte Carlo optimization, it's all about the following problem. You've got some, you have some parameter of a distribution that you want to choose so as to minimize an expected value. Like expected value of your social welfare function, of your objective function, given that distribution. This is, in general, I could write this down, this function, in many, many cases. I couldn't for the wind tunnel test because I can't write things down, but in other cases I can. But even when I can, when this is a high-dimensional nasty integral, finding that theta directly is really, really hard. So what these engineers have come up with is a beautiful idea. You importance sample. Do people know importance sampling for Monte Carlo methods? More or less some, okay. Well, the basic idea is really simple. A standard trick which gets you so very far in life, it should be like a bumper sticker. Multiply and divide by the exact same quantity. And nothing changes and everything changes. You multiply and divide by an appropriately chosen sampling function, h of x. You're now sampling, rather than taking don't try to take Monte Carlo samples of this, what's called simple sampling, to try to estimate that expectation. Excuse me. You instead use your sampling distribution, and then what you do is you form your Monte Carlo by looking at that part there, so that this you approximate with this, where h of x is the distribution used to sample the x. You can then, this is just a sum. Very, very often you can just directly find the theta that minimizes that. So this is the technique called Monte Carlo optimization in the literature. You can go Google it. It's got nothing to do with me. I was surrounded by engineers, so I'm just going around stealing ideas. And it's far, far easier than trying to figure that out because you're just a sum. Everybody with me? This is almost like a bit of a new talk. It's further away from naturally inspired, but it's addressing it's going to be, as you'll see, address the data aging problem. Okay? Now, and here maybe this gets back to Una May's original question. Supervised machine learning. We want to find a theta, parametric supervised machine learning, that minimizes this. That's your loss function These are your inputs, X, and this is whatever your noise process is. These are your outputs, Y. You want the theta, namely the fit, that minimizes this. And you're doing so with a training set. Notice, just one day while you're sitting around in your bathtub playing with your rubber duckies, it occurs to you that this integral looks a hell of a lot like that integral up there. Moreover, what these folks are doing here is that they're looking at a sampling of the underlying distribution, and they are finding the parameter that optimizes that empirical sample. Well, that sounds a hell of a lot like having a data set formed by sampling this and then trying to find the theta that minimizes the expected sum of loss values. And in fact, they are equivalent, identically equivalent. Here's the dictionary. Monte Carlo optimization, if you are doing Monte Carlo optimization, not general arbitrary kinds, but if you're doing Monte Carlo optimization, all these variables, here's what they are in supervised machine learning. Therefore, here's a problem that you might face when doing Monte Carlo optimization, and here is the machine learning solution you can use to improve Monte Carlo optimization. A dictionary. Stealing ideas from different fields. I'm there. Whenever you can, do it. Okay? We, by the way, if anybody has students who want projects, I'm going to be showing you how to do the experiments we've done for a very few of these, but there's vastly more. We've not done this entire table, and there's probably many more things you can do in this table as well. We've not done more than just a couple of them. Those ones have worked very well, though. First, I'm going to show how to minimize the variance. So this is all a bias variance kind of a problem. We've got a data set that we're using to make an estimator of what theta is actually the optimal one. There's going to be a bias, which means how far off is my expectation value over data sets, but there's also going to be a variance. How much is my choice of theta going to bounce around as I go from one data set to another random data set? How do we reduce the variance in machine learning? We use what's called regularization. It's a prior if you're a Bayesian. Techniques like Bryman's bagging are one powerful way of doing it as well. So, given the time I have, so what does that mean? The regularizer. Well, what's the kind of a natural regularizer for a distribution? In other words, what's the kind of thing that if it had a large value, your distribution would in some sense be smooth? Hey, simulated annealing does that. It's an entropy. So this is where we're starting to get back to the previous ideas of how it is that simulated annealing is playing games with distributions. Simulated annealing is regularizing. It's not actually doing this importance sampling. It's not that sophisticated. But simulated annealing, by using the temperatures are regularizer. And just like you change the regularization penalty as you get more data in supervised machine learning, in simulated annealing, you reduce the temperature as you get more data, because the regularizer term should be weighted less, just like in supervised machine learning. Identical. 10 minutes. Okay, cool. Now here's one that's going to probably be a little bit more stretching of one's creativity. How do we set the temperature? Fine. You've got this thing here, and in simulated annealing, they have this thing that I refer to as the annealing schedule. You just reduce that value, the temperature, with time. Based upon what? Based upon the fact that a bunch of people over a bunch of beers said, hey, why don't we do this exponentially? Oh, cool idea. Let's go with that. Can we do it a little bit more principled way? Well, how do we set, what's the analog of setting a temperature? In other words, setting a strength of a regularizer. In other words, setting the value of a hyperparameter. That's what it would be called in supervised machine learning. How do you set a hyperparameter? That's what the temperature is. I know, I use cross-validation. Well, what the hell does cross-validation mean in the context of optimization? Let's try it out. Just whenever you come across new math, the thing is to not try to think about what anything means, just plug and play and see if you can get the answers. And if you can, then afterward you can go back and try to internalize what's going on. But just plug the things in and see if that'll get you there. Okay, so I'm supposed to be doing cross-validation to be setting a temperature in MCO with an entropy regularizer. Let's say that my distribution is a single Gaussian and theta is its width. Let's just say that's my problem. What in the world does this mean? Well, what it would mean is that just like with cross-validation, as you get more data points, you can change the hyperparameter. In cross-validation, you should, in fact. In this context, it would mean you're doing simulated annealing, but you're not having a prefixed annealing schedule. You are auto-annealing. You're adapting the temperature as you go based upon the data. And here is what happens when we tried this for a particular, I think it was the Rosenbrock objective function we were trying in this particular case. You can see what the algorithm was doing. This is inverse, it's beta, so it's inverse of the temperature. At first, the temperature was very, very high. Then we start to cool down. Then, based on cross-validation, the algorithm said, whoop, folks, you've actually cooled your temperature too much. Back it up, reinflate, reheat things up. You got to go back to be doing more exploration, a little bit less exploitation, and now resume things. So this is the kind of behavior we find. And what we then did in these experiments, we had an adaptive temperature, and we had some runs where it was only adaptive temperature, some where we were using bagging and adaptive temperature. We consistently found the best performance. This is function calls, and here is you want your expected G to be low. This is your number of function calls to evaluating G. We found this is the best fit exponential. So this is cheating. This is God coming in, talking to you after a few too many beers, and you're saying, I'm going to go with an exponential. God, dude, what actual exponent should I have for my exponential? He said, well, the best you're going to do by looking over all 200 runs is to go with the following. Okay, folks, we're going to go do simulated annealing with this particular annealing schedule. That was the best possible exponential annealing schedule. Using cross-validation, we did better. And we found that kind of behavior consistently. Any kind of a parameter floating around, anything like Monte Carlo optimization, you can use cross-validation. Here's another example. How set the number of components in a mixture model? If you want to really squint, this is equivalent to saying how many species should I have in my genetic algorithm before I prune some out if I'm trying to find the one that has the highest fitness. Cross-validation automatically set the number of political parties, the number of species, et cetera, et cetera. And here we're now going to be seeing an example of it. So what you're going to be seeing, I've got to get this movie to work. This is a heat map. Blue is the best that you want to be. As you can see, it's a kind of a funky underlying objective function. This is starting. It's a mixture model of 5 Gaussians. You can actually see their shapes. The parameter theta is giving you the shapes. These are the isoclines of the Gaussians. So these are indicating the overall Gaussians. It's a mixture of those 5 Gaussians. We're trying to fit it to be concentrated. Remember, everything is about changing your distribution. We want it to be concentrated among the best possible points. The X's are the sample points so far. As this goes, you're going to be seeing new little X's coming in, which is going to be samples of the distribution of these Gaussians at that time. But then you're also going to be seeing we're using cross-validation to actually be updating the number of components, number of species, number of political parties, whatever you want, and it's going to be changing. So can I even get this to work? There we go. So now we've actually settled onto their 5, and they're looking at different parts of it. Whoops. We almost just joined. Now we just did. We're down to 4. And now that one's scooting over. We're now down to 3. And this is the best area over there. And if we kept running it, eventually it got down to 1. Oh, it is still running. And now it's down to 2, and now 1. The number of components in your optimization algorithm where you're using a mixture distribution changes because you're using cross-validation. Una May.
I wonder if it might be more appropriate to think of it as adapting population size rather than species in a genetic algorithm.
There are scare quotes around either of the above. It's not just population size, it's where the populations are concentrated. That's the sense. They have very different kinds of genomes if we're going to be really taking huge amounts of license, so to speak, with the terminology. But yeah, this is adaptively doing it, just like with cross-validation.
So in evolutionary algorithms, we often have self-adaptive mechanisms that we subject to evolutionary selection pressure.
That's an interesting idea.
Or it could be just the initial one, but this is saying, well, the evolutionary selection pressure could be replaced by an external cross-validation test, and that cross-validation test is going to tell you whether your adaptation rate needs to be back down, moved up.
Yep, and moreover, because that's a dictionary, it's pointing both ways. It is kind of like a category theoretic isomorphism. What that means is that the ideas that you just talked about, while adapting the adaptive mechanism, maybe we could translate that over into machine learning, where it would be adapting the cross-validation algorithm, which actually touches on other topics and relates to what's called stacking. But yeah, that dictionary is a very, very powerful beast in and of itself. And as I say, we've only looked at these 2 things primarily, bagging and regularization and cross-validation out of that entire table. So future work. Go over and over. There's tons of stuff here. And yeah, I'll end it there. I've got 0 time, I believe.